And here we are in our third nightly video. And of course, we're to do mathematics and physics, and we did some early stuff. But what we're going to work on has to do today with something new. We're going to look at something called significant digits. Significant digits. Significant digits, what are they? Significant digits aren't important. They don't matter. So we had to do in chemistry or something. They don't matter. I'm going to get a brand new custom dog collar for my dog Cookie. So I'm going to use this, and there we go. I need exactly that size of dog collar. I got my standard here, the end of this end. I wrapped it around her neck, and right there, that red point is what touched. So I have it stretched out straight. Let's go ahead and put a ruler next to it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh wow, 18 and about 18 and a half. 18.5 inches, 12 inches in a foot. I want to know how many feet my collar has to be. 1 times 12. 6 remainder, carry down to 5. 5 times 12 is 60. Oh, and a decimal here. So 1.5, well that rounds up to 2 feet. 2 foot diameter collar. I gotta get a 2 foot diameter collar. Got it. What I just got in the mail, it's my brand new collar, exactly like I ordered, 2 feet. 2 feet. This is gonna be perfect. I can't wait to take my dog for a run now. Okay, Cookie, let's go. I put this on because we have leash laws here. You're not allowed to just go anywhere you want. Whoa! Houston, that's right. We're going to need the part. Could you double check? Roger. We're going to go back to mission control and see if they can confirm that that's the right part. I don't think it is. What do you think? Get that salesman back on the phone. Well, don't worry, Houston. We got the piece you need right here. This should be fine to your specifications. I know it. I'll show you the math involved.
We take the finest quality, 1 meter, dowel, and then it's cut precision into 3. The math's pretty simple. Make that 10, 3, 3 times 3 is 9, carry another 0 down, 3 times 3 times 3 is 9, carry the 0 down.
There's 0.33333. They can go on 3 meters. This part will do just fine in fixing your problem. Well, that's the precision we need. It should fit right in here. If not, God help us all. Oops.
Significant figures are going to be very important, and keep in mind that significant figures express the precision of an instrument. And the precision depends on the gradations of the ruler you're using. So keep in mind that if that ruler that we're using has millimeters as the smallest lines, our understanding of the measurement is that it has to be between 14.50 centimeters and 14.60 centimeters. So if it has millimeters as the smallest line shown, it's precise to the nearest half of a millimeter, plus or minus, on either side of the measurement. Okay? And I'm sure you've worked with precision before, but the easiest way to do it is to work with this, okay? To combine this one here, okay, with the millimeters as the smallest unit, because we can only measure to the nearest half as big as the smallest unit, right? And then you can do a little bit more heavier thinking to get how we would work with this one, okay? But combine these two ideas. If the ruler has millimeters as its smallest line, then we can only have our our precision to the nearest plus or minus 1/2 of that particular dimension. Okay? Here are rules for significant figures that I'm sure you've worked with before. Non-zero digits are always significant. Final zeros written to the right of the decimal are significant. Zeros that are placeholders are not significant. They are going to be just simply telling us where to put the non-zero digits. And zeros between digits, I always call them zero sandwiches, are significant. Okay? So if we are dealing with 105,000, the 0 between the 1 and the 5 is significant. If we're talking about 150,000, 0, 0, 0, 0, none of those are significant. They are just placeholders. So 105,000 has 3 significant figures. 150,000 has 2 significant figures. Okay? Questions? Think about it. If you have any question you need help with, write it down. Okay? And we don't round until the end. That's one of the prime things you want to learn to do. Don't round off any of your calculated results until you're reporting your final answer. Okay, so keep in mind that significant digits are used to express the precision of your instrument. So you cannot be more precise than your least precise measurement. To add or subtract measurements, what you have to do is first perform the operation and then round off the result to correspond to the least precise value. So keep in mind, the idea is that you don't want to round off until the end. Okay? To multiply or divide measurements, you're going to perform those multiplications and divisions and then keep the same number of significant digits as the least precise measurement. Significant digits are considered only when we are measuring, not counting. Again, don't round until the end. Now the last part of our section today is scientific methods. Scientific methods are varied and do not always include every part of what you generally look at as a big list of the scientific methods. A scientist works with an idea very often that can be worded as an educated guess called a hypothesis. So we have certainly talked about the relationships between different kinds of variables, and we can talk about how we think based on what we know is going to happen. The hypothesis is then tested by many experiments, and when they pass muster and the experiments verify the hypothesis, although it can't prove, it just simply verifies. One thing to remember in physics is if you have a hypothesis, all you need is one counterexample to disprove it, okay? But you will never prove it totally because you might always think, well, maybe I just haven't found that one counterexample. As long as all experiments keep showing that the hypothesis is valid, scientists can use the hypothesis to build models, laws, and theories. An idea, equation, structure, or system can be used as a model, and computer models are absolutely vital for scientific and physical kinds of experimentation. If the new data don't fit, then they basically are going to first of all look at the actual data themselves that just came in and see if there's any problem with that, and model. And they will also re-examine the model itself. So we do a very, very exhaustive kind of testing process. It's very open. It's the scientific community working to basically make sure that our models are valid. A scientific law is a rule of nature that sums up related observations to describe a pattern in nature. I brought this up, for example, because people from many centuries have known that the angle that light comes in to a surface at, measured with the normal, which is the perpendicular line here, right here, this is called the normal to the surface. Normal in physics means perpendicular. That the incident ray, the incident ray is going to come in at a certain angle that will be exactly the same as the reflected ray. And so the angle of incidence is equal to the angle of reflection. If you throw a ping pong ball, or let's say a tennis ball against a garage door, it's going to come back. You're going to know where to anticipate it. Tennis, for example, is built on the law of reflection. So this is the way something becomes a law. People know it to be true, and related observations are always going to describe this pattern in nature. A scientific theory is an explanation that is based on many different observations and supported by experimental results. It basically explains why things work as they do as compared to that things work as they do. Theories usually serve as explanations for laws. And they can all be discarded as long as people agree that perhaps that explanation does not fit anymore. In scientific use, if something is very well supported, that's when it will be called a theory. We generally say that a explanation becomes a theory only when the last of its opponents dies. So things like Newton's laws and things are laws of, laws that Newton has used to describe nature. If we talk about theories, we generally are very much understanding that no theory is truly complete. Every theory is always going to have room to accept or reject parts of it based on future kinds of experimentation. So there's our summary. Why study physics? Well, you've come to the right place if you want to study physics. Physics is extremely important, and it's not just because I say so. We need math skills. We need to bring our calculator every day. We've been SI systemed to the hilt, so hopefully we understand that. We are going to be applying significant figures to determine precision, and we're going to be considering dimensional analysis and how that can help us to understand how to work with different kinds of formulas. Okay, we'll see you tomorrow.